I continue with the Penrose diagram for the black hole. Actually, there is a coordinate transformation in this metric. Let me do the following. If I make the following change, rho is equal square root of 1 minus r g over r, and consider the limit r going to rg, this metric becomes approximately equal to the following. It's rho squared dt squared minus d rho squared minus rg squared d omega squared. So you can see that its two-dimensional part is very similar to the, it's actually coincides with Rindler coordinates. That corresponds to the fact that if you are very close to the horizon, and the horizon is big, so this actually can be approximated by flat space in case if Rg is huge. So you are hanging on top of the horizon in its vicinity, you see homogeneous gravitational field, which is equivalent to eternal acceleration. So, of course, gravitational field of a black hole is inhomogeneous because it's spherically symmetric. The lines of gravitational field are like this, but in vicinity of the horizon, it's almost straight. So it's almost homogeneous. Okay. As a side remark. So you already see some properties of the black hole by looking at the Rindler spacetime, Rindler coordinates of flat spacetime. So this is flat. Meanwhile, this is curved. Nevertheless, this approximately describes the curved spacetime because in local vicinity of any point, you can consider your spacetime as almost flat. Everyone who thinks that the Earth is flat should know that. Okay. Now I will make some coordinate transformations which allow me. So I want to write coordinates which cover entire space-time. Entire space-time. What that means? You see, as I told you, Rindler coordinates, they cover only part of Minkowski space-time, only this right quadrant. This metric also covers not the entire space-time, but only its region for r greater than rg. But I want to write metric which covers entire black hole. Here I should notice that this metric is also static, so it's invariant under the time translations, but also under the time reversal. Actually, being formulated in Hamiltonian form, Einstein equations possess the following property. For any solution, you have its time reversal also solves this equations. You see? So, but meanwhile, this guy is time reversal of itself. That's the reason this Schwarzschild solution probably is unphysical in the following sense, that it describes, well, it describes eternal black hole, first of all, and moreover, it contains also white hole on top of black hole, and we will see that. So real black hole is created in the collapse process, you see? And in that case, that created in the black hole, created as a result of the collapse black hole is not time translation and time reversal invariant. That's entire solution. If you take it from minus infinity to plus infinity, it is not time translation and time reversal invariant. Time reversal of the creating of the solution that is describing collapse is just a blow, explosion, inverse process, explosion, also the solution of Einstein equations of motion. So one more thing, but this metric does describe approximately the solution which is the result of the collapse. So if you take the solution describing the collapse and take its eternal form, I mean the form when you take time to infinity, it just corresponds to this, looks like this solution. Locally, it looks like this, not for all times. You see? Okay. Now, how do we know how to cover this solution entirely? How we will all space-time, not only how we will find the coordinate system that covers entire space-time. You should embed your space. To do that, one of the ways, the way that I know, is to embed your space-time into higher dimensional flat space-time as some hypersurface. It can be done with any space-time. Actually, any metric can be understood as embedding. Like, for example, do you understand what means embedding? I mean, like, for example, sphere. Sphere is a result of some embedding. Well, for example, this two-dimensional sphere is the result of embedding of this surface into Euclidean, three-dimensional Euclidean space. So to embed the sphere, it's a two-dimensional sphere. You see, this is a whole collection of whole points, x, y, z, that obey this property. So like equal distance away from the center of this space. Okay? So this is a two-dimensional surface embedded in three-dimensional space, one equation. The sphere is very symmetric. That's the reason you need one extra dimension to describe its embedding. If you have a generic metric, G mu nu has a lot of parameters. So naively, you should count the number of parameters in generic metric and add them to the dimensionality of your space-time to understand how much extra dimensions you need to embed your space-time. That's naive counting, actually works frequently. This space is not that symmetric as sphere, so, and not very generic. It's spherically symmetric at least. I mean, spherically symmetric is not that symmetric as sphere, by the way. I hope it's clear. I don't know if people understand me. You see, for example, analog space-time analog of this guy is the following metric. It's actually essence of the discussion of the first talk. This metric, inflationary metric, is highly symmetric space-time. It has as many symmetries as flat space-time. Looks very strange, but it does have as many symmetries as flat space-time. It actually can be, if somebody knows what means weak rotation, after weak rotation, this space-time can be mapped to sphere. And to embed it, you need one extra dimension. This is called de Sitter space-time. De Sitter space-time is very symmetric, so you need one extra dimension to embed it. So four-dimensional de Sitter space-time can be embedded into five-dimensional flat space-time. Black hole doesn't have as many symmetries as this one. So this metric has less symmetries than this one. So it can be embedded in six-dimensional space-time. I'm not going to do that because it demands some extra efforts, et cetera, and actually we don't need it. So, but that is the way you understand how the entire space-time looks like. You should embed it into higher dimensional space-time as a hypersurface. Now I will do, so for example, you see this metric covers the region R greater than RG. I wrote to you the metric like this, RG times dV squared plus or minus, I don't remember, dV or dr minus r squared d omega squared. So you see this is the same space-time, but written in different coordinates. And this coordinate system is applicable for r greater than 0, for any r. So how do we know that this metric covers entire space-time or not entire space-time? You see, this metric covers only part of entire space-time. This covers more than this one, but does it cover whole space-time? That's the reason I initiated this discussion, as I told you. Now I am going to write to you Kruskal coordinates which cover entire black hole space-time. Meanwhile, this metric doesn't cover entire space-time, interestingly enough. So you see, this metric is not time reversal invariant. Here, in a sense, you have another time. It's called actually light con time. Here, V plays the role of time. If you change V to minus V, the sign of this term changes. So there are so-called ingoing Eddington-Finkelstein coordinates and outgoing Eddington-Finkelstein coordinates. And these are two different types of space-times, by the way. As I promised to you, if you have a solution of Einstein equation and make this map, you get time reversal of it. This is self-time reversal. It's time reversal of itself. This one is not time reversal invariant. Nevertheless, this metric doesn't cover entire space-time. Now I will write for you the metric that covers entire space-time. And how people guess it, Kruskal and Zekerish, if I correctly understand, they did that via this mapping, as I told you, in mathematically rigorous way, and made sure that the coordinates that they used covers entire space-time. Okay, now I'm going on. So I did the following coordinate change, I remind you. 1 minus rg divided by r dt squared minus dr star squared. Remember, I did this change. R squared d omega squared. Here is, this is assumed as a function of r star, some complicated function, which is solution of a transcendental equation. Then I can change make the following change: dt plus t plus r star I call v, t minus r star I call u. Okay? Now one can easily check that t is just v plus u half, r star is v minus u half. You see? And from here, knowing that this is r plus rg, do I correctly actually write this tortoise coordinates? Yeah, correctly. Rg log of r divided by rg minus 1. So, here essentially you now understand, solving this equation, you now can understand the following. You essentially have the following thing: rg, r as a function of uv, that solves this equation, du dv minus r as a function of uv d omega squared. Do we have another pen? Because soon this will vanish. Okay. So now we want to understand what to do at the horizon. I'm using a bit different reasoning, a bit different way of reasoning to derive these Kruskal coordinates, those which cover entire space-time. Be patient a little bit, because probably it's annoying that I'm spending too much time on this rederivations, etc., etc. I'm just explaining to you technical details. Then you will understand the reason why I did this. So you see, I want to understand what to do in the vicinity of the horizon. I want to introduce such coordinates which allow myself to move through the horizon. How you call it? I want to use such coordinates which are smooth at the horizon. Smooth in the following sense, that the metric in those coordinates doesn't have peculiarities at the horizon. So you see, when this is when we are approaching the horizon, this is approximately 0. So now let us see what happens to this equation. You can see that as r approaching the horizon, you can approximately substitute this by rg, approximately. And then it's very easy to solve this equation. Namely, you will have this factor, exactly this factor, expressed through these quantities. That's very easy exercise. So you approximately in the vicinity of the horizon can write that this is approximately equal to v minus u divided by 2rg, something like this. That is a hint. You see, it's very easy exercise that I can, for example, instead of dv, so I can use the following thing. dv I can name as dv big, and as du big. You see what I'm doing? Because if I make such a coordinate change in the vicinity of the horizon, this metric becomes very simple. This metric becomes flat. This is flat metric. So if I move backward, that I, instead of u and v, use t plus r, t minus r, I get just dt squared minus dr squared. This is flat metric. So I found such coordinates which make my metric flat at the vicinity of the horizon. I told you that at the vicinity of any point, I can make my space-time looks almost flat. So I always can find some coordinate system which is flat in some local vicinity of any point. You see the reasoning? So that gives me the idea what to do. Okay? So from the very beginning, instead of doing all these horrible derivations, let me make the following change. Let me use the following coordinate, u big, which is minus 2rg e to t minus r divided by 2rg, r divided by rg minus 1/2. And v, like this, 2rg exponent to t plus r divided 2rg, r divided by rg minus 1/2. So if I do such a transformation, this metric becomes as follows. Rg divided by r as a function of uv. Function of uv as follows. We will see in a moment. Multiplied by exponent minus r as a function of uv divided by rg, du dv, du big, dv big, minus r squared d omega squared. So you see this metric has no any peculiarity at r equals to rg. As we approach the horizon, r becomes equal to rg. This metric doesn't degenerate. So I can use this coordinate to move across the horizon. They are applicable even for r less than rg. It is only important that r and t are applicable for r greater than rg. You see this square root is defined for r greater than rg. You see what I mean? Situation, let us return back to the very beginning of my lecture, previous one, the first one. Let me explain to you what I'm doing. Before I will do that, sorry, I shouldn't have erased. So this is
But the square root means that your coordinate became complex after.
That's exactly the point. Not to make it complex, I can use, you see, u and v. No, that's exactly the point. V is greater than 0 for r greater than rg, always greater than 0. And u is always less than 0 for r greater than rg. But I can extend u and v beyond these regions, but they will not be related to r and t anymore. You see? They will not be related to r and t anymore. That's the reason I told you that let us return to the very beginning of my talk. That's the reason I started with accelerative motion.
Is some kind of analytic
No even need for that. No even need for that. Just wait 3 minutes. Just 3 minutes. So you see, let us see what are the constant in terms of these u and v coordinates, what are the curves of constant t and r. So if I divide u by v, I get the following. It's exponent minus t over rg. You see? So constant t lines are straight lines. Moreover, if I u squared minus v squared, make u squared minus v squared, oh, sorry, no, u times v, sorry, u times v. If I multiply u by v, I get just a function of r. I get minus 4rg exponent of r divided by rg, r divided by rg minus 1. So you see, these are straight lines and these are hyperbolas. So that's a very simple exercise. So let me draw the space-time in terms of, you see u and v are coordinates like, let me write it. Let me draw r and t, oh sorry, x and t. U and v are directing like this. This is, I think, u, and this is, I think, v. So you see, my space-time, this space-time covers only this quadrant, negative u and positive v. You see? No, it's big T. Okay? X, sorry, X, not R, X. So constant T, constant small t lines are straight lines. Constant R are hyperbolas. Situation is extremely similar to what I draw to you. at the very beginning of the first lecture. So let us return back to that discussion to understand what is going on here. So I am erasing this. So what did I do at the very beginning of the previous lecture? I will restrict myself to two-dimensional case first. I did the coordinate change like this. T rho sinh of tau, x is rho cosinus of tau. And I got the coordinate system like this. Right? So this was x, t, and rho. So these were the constant rho curves. These were the constant t curves. Now, you see these coordinates for rho greater than 0, they cover only this quadrant. For rho less than 0, this is rho greater than 0. For rho less than 0, they cover this quadrant. You see what I mean? Now, if I want to cover this and this quadrant, I can use another coordinate change. So I flip. So I just I use t equals rho prime cosinus t prime and x rho prime sinus t tau prime. You see? Then I cover this quadrant. Just because cosinus is always greater than sinus. So t is always greater than modulus of x. This is this quadrant. For rho negative will be this quadrant. So you see? So these coordinates I can use only in this quadrant, but t and x I can use everywhere. T and x I can use everywhere. Rho and t only in this quadrant or in this quadrant. Rho prime and t prime in this quadrant and this quadrant. So somewhat similar happens here in the black hole case. So if I, for example, consider this region, I have some t and x here, but they will not be expressed through rho and tau. They will be expressed through other coordinates, rho prime and tau prime. I'm just stressing this point here. Okay, now with the black hole happens the same situation, essentially. So instead of, I'm looking for this guy, but I already have this guy. Let me keep on doing only two-dimensional part. So I forget about the other two dimensions. You see what I mean, right? I am looking for this guy. And for this guy, I am writing to you that this is r, which is some complicated function of rg divided by r, which is complicated function of u and v. Here is minus r divided by rg du dv. So this is analog of this. Meanwhile, this is analog of this. I remind to you that u is constant. So multiply, if I multiply here is just 4rg squared r divided by rg, r and u divided by v is exponent of minus t divided by rg. Okay, this is a coordinate change I made. So r and t coordinates are applicable only in the region where u is less than 0, v is greater than 0. And constant t lines are straight lines, constant u lines are hyperbolas. constant r lines, sorry, are hyperbolas. So, but I can use these coordinates also in this quadrant, and in this quadrant, and in this quadrant. But to cover these quadrants with some other coordinates of the type of t and r, I should use t primes and r primes, etc., etc. You see? So absolutely similar situation. Okay. So my, you see, I don't need analytical continuation. I don't do analytical continuation. I didn't do that here, and I don't do that here. Okay. Now, let us do the following. Let us use r prime and t prime coordinates also here, their owns for each quadrant, separate r and t coordinates. And what we will see here in this quadrant, that there will be some ultimate hyperbola here corresponding to r prime equal to 0. This ultimate hyperbola corresponds to the singularity of the metric. There, the invariant r mu nu alpha beta squared blows up, just tends to infinity at this position. So there will be some hyperbola here also. You see what I mean? There is no space-time beyond this r. There is no space-time here and here. So from the whole plane, I cut out some region bounded by hyperbola from below region and from above. So this is my space-time. So the relevant part here is two-dimensional again, here and here, it's two-dimensional part, and I can make Penrose map. So you see, I can in Penrose map I don't care about the conformal factor. So I can always drop this conformal factor. Then this is just a flat space-time with cutted out curves. You see? So now if I perform the same conformal transformation as I did for the flat space-time with this guy, what do I get? I get a fantastic thing. I get the following. Essentially, I get the same rectangle, actually not even a rectangle, square. The same square, but with the cutted out sorry, I'm a bad painter. This is light-like line. This is light-like line. Let me erase and draw again a bit more carefully. I want to draw a beautiful picture. So, like this, and I cut it out this. Sorry? No, this is X, big X, and big T. Meanwhile, U and V are just linear combination. U is T minus X, V is T plus X. So they are directed like this and like this. U and V coordinates are like this and like this. Okay, so no, my space-time doesn't contain this. And the metric blows up at these curves. I deliberately wrote them wavy to stress the fact that here something blowing up happens. It's a singularity where the invariant is blowing up. This is Penrose diagram of a black hole. And I can describe properties of the black hole just by looking at this diagram. And I will describe them in a second. But let me just stress the following thing. This is, you see, this is my constant R curves were hyperbolas. They are like this. They are mapped to this thing. This is constant R. Constant T curves are like this. This is constant t. Those straight lines are mapped to these curved lines after the conformal map. Okay, these hyperbolas degenerate into these straight lines. You see, the equation for the hyperbola was like this. This is some function of r, which becomes 0 as r equals to rg. So these hyperbolas degenerate to these two straight lines at r equals to rg. So this is r equals to rg. This is horizon. Similar to the horizon I had in Rindler spacetime. But now this is property of spacetime, not of the observer. You see? Let us look more carefully at the situation.
Why it's named as diagram, but not?
I mean, name it the way you want. We can name it chair if you want. Penrose chair. Does it change anything the way? Somebody called it, actually I think Parker was one of the first who drew these diagrams, even maybe before. For some reason, I actually never met Penrose, but I've met Parker. And Parker is a peculiar figure. Recently he published a paper on particle creation, which he actually wrote in back in 60s. But never published as a separate paper, as far as I understand. So he published this. I think it's not a paper even; it's his thesis. He published his thesis. I'm not even sure that he did himself. Probably somebody. I don't know if he's alive. I saw him 20 years ago, actually 25 years ago. But for some reason, everybody remembers about Penrose. Nobody remembers about Parker. I don't know. Okay, yeah. By the way, about cosmic microwave background. When I was a student, there was a rumor among the students. I think it's established fact. There was some teacher at Moscow Institute of Physics and Technology, MIPT, some lecturer who was in 50s or 60s were going to prominent figures and saying that on radio he hears microwave background. He was interpreting. Nobody believed him. They were thinking that he's crazy. I actually, if I Google it, I will find the name of the guy.
Maybe that's true, right?
Yeah.
It could be.
He actually did. He was going after, I don't know, even probably Landau, and they thought that he's crazy.
The important thing is the temperature. He measured the temperature.
Yeah.
Everybody knows there's such a noise.
Not simply that he interpreted this noise as a remnant of the beginning of universe. That was important. He understood that this is not a noise from other radio stations. It's present everywhere. Okay, nobody believed him. So this is a horizon, r equals to rg, and this is singularity. People usually write it r equals to 0, but it's actually not the same r as here, but just in case. Okay, now let us describe the property of the black hole by looking at this diagram. Okay, I will erase it and draw again, just to use less lines in the figure. And I draw a bigger one. These are all light-like lines. This not the wavy one, but the straight lines are light-like. They are 45-degree angle with respect to. So this point corresponds to t equals to plus infinity. This point to t equals to minus infinity. This point to r equal to infinity. This is r equals to rg. This is r equals to rg. Now, suppose you are considering a guy who is hanged over the black hole. So it stays at fixed r. The guy's world line is like this. This is r constant. You see, this guy never will, anyone who is beyond the black hole, outside of the black hole, his world line will be something like this, obeying the properties that it is space-like, time-like. You see what I mean? So this line is time-like, this line is time-like. Now, you will never receive, suppose there is a source of a signal somewhere here, emits the signal. The signal will go within the light cone, so it can go anyway here. So it will never go outside. So this is a black hole. Here the situation is opposite. Source from here will send signal and it will come out, but you cannot send signal here. This is white hole. This is black hole. As I promised to you, the space-time that I'm describing contains both. And now, you see this curve is not t constant. This curve is not t constant. This curve is r constant. So it's in future infinity. That's important to answer your question about delta function. Delta function, delta of r, means that you took t constant, time, some Cauchy surface, and put at it some source. This is not the line at which you can put the source. You see, it's not the Cauchy surface. I hope it's clear what I mean. Sorry, no, it's other way around. I confused you completely. It assumes. Okay. Maybe I shouldn't go into that. Let us postpone that. I will discuss it a bit more carefully. So essentially, I wanted to explain the reason why you cannot put delta function here, even without any calculation. Huh?
What is a white hole?
Sorry?
A white hole.
Yeah. White hole. And this is black hole. And now suppose you drop someone into the black hole. So there is someone who is staying at radius, at constant radius, and there is someone else who just jumped from that radius and went into black hole. First of all, this guy inevitably end up in the singularity. Inevitably, because its line always, how you call it, it should be time-like, so it should be within the light cone, so it's directed there. Inevitably, you cannot avoid falling into singularity. Avoiding falling into singularity is the same as avoiding next Monday. See? That's the first thing. Second, suppose this guy emits light rays towards the guy which is hanged over the black hole. Suppose it emits in its proper time within every second. Every second there is a signal. But this guy receives the emitted signals later and later and later. And the distance grows indefinitely, infinitely. So the light ray emitted exactly at the point of crossing the horizon will be received by this guy at t equals to infinity. So will never be received. That's without even a calculation. I show to you on the Penrose diagram the following phenomenon, that you can fall into the black hole, cross the horizon within finite own proper time. Meanwhile, someone outside of the black hole will never see you crossing the horizon. Okay, then the usual question which I actually asked myself when I was a kid and was reading when I was high school boy, I was reading some books, popular science books on black holes. If nothing can fall into black hole within finite time, does the black hole create within finite time? Or you see something which is in eternal fall? Well, on our devices, we will not distinguish two situations. because what we measure is some radiation coming out from the very vicinity of the black hole. Two situations are indistinguishable in a sense, if how you call it, because we look at the blue shift or red shift of the radiation, and we will not distinguish the matter crossed the horizon or it's present in the very vicinity. So the radiation essentially having the same properties outside. Nevertheless, does the reason why I'm asking this question is just to discuss with you physics, because this whole so far was mathematics. I was writing equations, etc., drawing for you pictures with the use some of those equations, etc. But I never named the approximation at which this is valid. Well, first of all, I used general relativity, so all these figures and formulas are valid only when I use general relativity. Yeah.
May I ask you a question about the structure?
Sorry?
May I ask you the question
Yeah.
about the structure?
Yeah.
So when you consider the light is going to the black hole, and then we draw the lines for the light, like for example, lines, at some point they reach the point, the angle, right? So what happens in this moment? Because I guess
What angle? Angle between what and what?
in between space to infinity and singularity.
Yeah, but this light ray is always 45 degree
Yeah,
with
exactly.
respect.
And
So
at some point it goes to this angle.
no, light rays end up here.
Not, okay, maybe.
They never go to this point. Just because they are 45 degree, this is 45 degree with respect to the vertical axis. This is also 45 degree, and every light ray is 45 degree with
Yeah,
respect.
so then 45 degree, and at some point they reach the.
They reach this
Right.
line.
Yeah,
They never reach this point. Well, only the light ray which is emitted along the horizon will reach this point.
But the guy still doesn't reach the.
Sorry?
The guy is still at like at the point when maybe we can go.
Okay, I mean, I don't understand your question, but I have a feeling what you want to ask. But let us wait until you formulate the question in proper way.
Can I ask
Yeah.
what there was white hole?
White hole. Yeah.
And I want to question, isn't white hole just a theory? Because I heard the white hole can't exist because it conflicts with the second law of thermodynamics.
Okay, first of all, thermodynamics and second law of thermodynamics is not a fundamental law of nature. But that doesn't, again, there are too many things to say about what you say. First of all, second law of thermodynamics works when you have a closed system. With gravity, you cannot close any system, essentially. So what means thermodynamics in the presence of curved metrics and dynamical gravity is a separate, very hard question. So I wouldn't use this sort of argument against something like that. Nevertheless, I don't know whether white holes or not exist, but I told you that the real black holes are created as a result of the collapse. Meanwhile, I draw for you the picture for the eternal black hole as if it existed forever. So I don't think that Schwarzschild metric is applicable for any times. So physically, it doesn't exist for eternity. You see, physically, black hole is created. So, for example, you see there is you know Maxwell equations, right? Maxwell equations have the following funny solution. Even with zero in the empty space, you don't have any charges, anything. You have a solution that E equals constant. Constant for all times and constant for all x's. Everywhere and always constant. Maxwell equation has such a solution. Is this solution physical? Probably no. There are no, I cannot exclude that there is a universe. Actually, I can exclude because it carries energy, so it will curve space-time. So yeah, it's unphysical solution. So Maxwell equations, even Maxwell equations have unphysical solution, non-physical solutions. Nevertheless, they are solutions of equations of motion. Maxwell equations are correct, but they have unphysical solutions. So Einstein equations are even more complicated than Maxwell, and they have such a solution. But it's not physical. If you understand it applicable for any times and for any radii, you see? In real situation, you will not have a single black hole and for eternity. In real situation, you can have this between the plates of the condensator, but not for all times and for all x's. You see? Okay. So I hope I explained to you my understanding. Okay, let's discuss collapse. Collapse. I mean, we will draw a Penrose diagram of collapsing universe. Collapsing star. The diagram will not look like this. It will look different. So for that, I have to describe Oppenheimer Snyder collapse for you, but we'll do that quickly for the collapse. For the collapse, I have the following situation. Unlike this situation where I didn't have matter stress energy tensor, here I have a matter stress energy tensor. There is a matter that's collapsing, that creates the gravitational field. And this is a Penrose diagram of the collapsing star. So this is the body of the star, which is collapsing. And I have horizon. So for example, somebody static outside. So it's a spherically symmetric collapse, idealized situation. Spherically symmetric body which is collapsing. It doesn't create gravitational waves. Actually, good point to ask question. Why spherically symmetric collapse doesn't create gravitational waves? Does anybody know why military guys do not do antennas which are spherically symmetric? Then you can detect planes everywhere. Just spherical antenna, you detect plane coming from that side. They, for some reason, create antennas, plates, directing in one direction. Like there is a rocket which can come from that direction, so let's put it directed like that.
These waves can annihilate?
Sorry?
These waves can annihilate?
Annihilate?
Yeah.
Waves annihilate?
Well, just I'm coming from reflected and transferred.
Reflected from what?
From this sphere.
Sphere radiates the waves. Sphere is antenna that radiates. How do you detect plane? You radiate radio wave, it refracted from the plane, comes back, and that's how you know that there is something going on there. So why don't you do the antenna spherically symmetric? To radiate in all directions, to detect planes and rockets coming from all possible directions. Not answer the question to you. It's a question to students. Okay, I formulate the question in a different way. I have a sphere, homogeneously charged, and it's breathing, spherically symmetric way, going like this, oscillates very rapidly in spherically symmetric way, always respecting spherical symmetry. Does it radiate?
No, the field outside does not change.
The field outside doesn't depend on the radius of the sphere. It's always the same as Coulomb field for a point-like particle, no magnetic field. If you try to understand how it happens, there are different ways to see that. First way, is to gauge away the field. You can gauge away if you know what that means. Or the other way is that there is an interference. So the antenna is actually had, как излучатели? Radiators, emitters. It's essentially like antenna is like this. It consists of, there is a fluctuation of a charge current going here and radiates radio wave. So if you have a hedgehog of these guys, they essentially, how you call it, interfere with each other and essentially cancel. So if you direct them in one direction, they, if the antenna is a plate, and these emitters are directed in one direction, they actually increase each other. But if you start to rotate, how you call curve it, they kill each other. Nothing, interfere. Interference kills the radiation. Okay, the same situation as you recall from high school, any spherical body, in gravitational case it's even a bit more complicated. So to have electromagnetic radiation, you have to have dipole moment changing in time. So you cannot have only charge. You need dipole moment. For the gravitation, it's even more complicated. You have to have also quadrupole moment. Dipole moment is not enough to radiate. So that's the reason if you have a spherical body, spherical mass, and it breezes, it doesn't radiate gravitational waves because it creates the same Newton field outside of itself. You see? So the metric will be, in a relativistic case, a relativistic generalization of Newton field is this metric. Whatever size of the sphere is, if its mass doesn't change, it creates such a gravitational field, no gravitational waves. So if you have a spherical symmetric collapse, despite the fact that the matter moves with acceleration, it doesn't create gravitational waves. So outside, so here, outside of the body of the collapsing star, you always have this metric. And at some point, this guy crosses its own horizon. So in proper, how we call it, in finite proper time, it crosses the horizon. But somebody hanging on top of this guy, on top of the collapsing star, will see the collapse, but will see this eventual stage of the collapse as slowing and slowing down. But now let me just stress one point. You see, I draw this. In what approximation I draw that I say that light rays are traveling along these lines? Which approximation I use? What do I neglect when I draw light rays saying that light ray is going along this line?
The lantern.
Huh?
The lantern.
What lantern?
So the light rays must be affected.
Affected by what? So does this line coincide with actual motion? Does this line precisely coincide with actual motion of the light rays? In what approximation light ray goes along this? It's called light-like geodesics. In what approximation light rays go along light-like geodesics? So, in what? When I neglect the fact that light itself carries energy. Light itself carries very tiny amount of energy. Very tiny amount in comparison with a black hole if I consider just visible light or radio waves, or even gamma quanta. Oh, of course, in principle, potentially, theory doesn't forbid to have such a gamma quantum which will have such an energy as a black hole has. But that's very hard to imagine that something like that happened in our universe. Although maybe in early universe. Okay. So these lines are not actually lines in proper sense. So light ray travels along this line only in the approximation that I neglect its own energy. So it's imaginary lines. So the question is whether if I emit a real electromagnetic wave at this point, whether it will stay always on this line. You see, it can itself participate into creation of the black hole, into the creation of its mass, or escape to infinity. Depends on the situation. So in real situation, light ray will not stand on this line. So it will either fall or go like this. But that's very hard to, how you call it, to calculate. So usually people neglect the energy carried by light ray and draw geodesics. So the situation with the real collapse is as follows. You will be receiving signal. You will be receiving signal from the collapsing matter as it approaches the horizon. But at some point, you will just stop receiving the signal. So that you can call the moment of creation of the black hole. But then the problem is that the horizon in that case to define is not an, how you call it, is not a, как это сказать, sorry. It essentially depends on the energy of this light. If you emit a signal from here, whether the signal participates into the creation of the black hole escapes to infinity depends on its energy. So to define the horizon, you have to essentially use the energy of the gamma quantum to define it, which is not a universal thing, you see? But nevertheless, the black holes are created within finite time, even from the point of view of outside observers. That's actually, this is here I'm discussing describing my own point of view on the situation. I don't think anyone else, although I never heard in the literature this sort of explanation. So, you should understand the approximation in what you write, formulas and all the pictures. So this is, so what else should I tell you? There are several things which I can tell you, but the problem is that I need more than 10 minutes for that. And probably at this point I will stop and answer the questions if you have. I lost you completely. So after all, black holes are not so complicated. It's actually a very simple subject, by the way.
Can we describe maybe merging black holes?
That's more complicated. You see, we don't know how to solve precisely three-body problem in Newton physics. When you have emergent black holes, you have situation with two bodies and the gravitational field, which is more complicated than the three-body problem. So we don't have exact solution for that. So, and moreover, Penrose diagram will be very hard to draw in that case because you have to single out somehow some two-dimensional part of entire space-time. But which one to separate? For spherical symmetric case, R and T. But for that case, there is no any symmetry. You don't know which coordinate to use.
But
So
numerically,
numerically, they simulate and solve.
the accreting similar.
Yeah. So of course you can solve to solve this problem. You use these equations and define the approximation in which you work. But even in electromagnetic field, for example, if you have two charges, you cannot solve exactly what happens. You solve in the approximation that they move not very fast enough and use radiation as a perturbation on top of their motion. You see, you first fix the curve it moves on, and then calculate for that curve intensity of the radiation. So this way, you estimate how much energy it loses and approximately describe how they move. So it's even in that case, it's a very hard problem. Actually, even in electrodynamics, there are very few exactly solvable problems. To my knowledge, actually, a single point-like particle. If you don't use external fields to, like you can solve problem for many point-like particles, but there is some extra force which keeps them at these positions. If you relax this force, they will start to move, and you don't have solution, exact solution. But there are approximations in which you can approximately solve. For example, drifting of particles when you neglect their radiation essentially.
the gravitational interaction is very slowly to discrete, but in for oscillator we have the growing interaction, but it is not the reason to move out second law of thermodynamics.
I'm not moving it out. Just let me tell you that the way I understand second law of thermodynamics, the growth of entropy, right? The growth of entropy follows from the fact that you use Boltzmann's kinetic equation, and here you have integral of collision integral. Using the Boltzmann kinetic equation, you can show that entropy grows. Always. Just you write an expression for the entropy and then plug it there, and from this equation follow this fact. But the problem is that this fact, this equation is approximate. So if you, for example, try to write kinetic equation in the presence of gravitational fields, you will not necessarily get this. So in each case, in some approximation, you will probably get approximate equation from which it follows. But it can happen that, like, I know the equation where it not necessarily follows. Any law of nature has, how you call it, is approximate. Any law of nature has limits of applicability. Even the energy conservation, who talks about the second law of thermodynamics? Even energy conservation has limits of applicability. Expanding universe doesn't have conserving energy. Well, it's true. In the zeta space, there is no conserving energy.
Well, the energy goes to gravity, no?
I mean, you cannot define even what means energy in case if there is no time translation invariance. You can define what means energy if you have either time translation invariance or asymptotically flat space, where you can approximately use time translation invariance. If you don't have asymptotically flat space and time translation invariance, sorry, you cannot define.
But you could always solve the energy into gravity, no? I mean, it doesn't have to really come from.
Like, for example, the photon travels through the universe and becomes redshifted. Where energy goes? Can you write an equation? I know what I mean. You see, I am like Lomonosov, believe in the fact that if there is something appears, if there is some increase in something, there is a decrease in that thing in some other place, or vice versa. But it's not energy. You have to be more careful to define it. You see, for example, there is a particle creation in de Sitter space. Where energy comes from? Nothing reduces.
I know, but
Not what reduces?
mass of the black hole.
Mass of the no. Expanding universe. There is a cosmological term. It's constant for eternity. You have a particle creation. You can heat your room without even, how you call it, perpetuum mobile.
What about electric charge? You mean there is no absolute energy conservation law? What about electric charge? Did it conserve in the expanding space, or it's another matter?
I didn't think about that, but the way I prove the conservation of electric charge, I can do that even in expanding universe, because there is no need, no use of the metric in it, in the derivation of the.
But you have to use, for example, the wave function.
Probably you should be. Yeah, well, probably you should be careful. Maybe there is a long derivative, and then. Okay, I like. Come on, this is a separate issue. I should think about it. From the scratch, the answer that it's also not conserved. But at least I made you to think. Actually, I think that particle creation in inflationary universe goes with decrease of the cosmological constant. But that's very hard to prove. Nobody believes me. No, not nobody. Polyakov believes me. Rubakov didn't. Starobinsky didn't. But, okay.
But I have a question related to the second thermodynamic law. Isn't, if I remember properly, Bechstein generalized this law to include the Hawking emission?
Yeah, but that's in concrete situation.
Yeah.
So,
entropy of the black
yeah,
hole
you
is
can,
not.
yeah. In the case of black hole, in flat space-time, you can have energy conservation because it's asymptotically flat. So you can have energy conservation, and you also have a second law of thermodynamics. So black hole also carries some entropy, and the total entropy is increasing. But again, you should specify the approximation in which you work. Every natural law of nature has limits of applicability. I draw these pictures with the use of general relativity. General relativity is not applicable in the very vicinity of the singularity. Singularity is something where you have infinite density sitting in one point, essentially, which is impossible. Physics doesn't have infinities and zeros. You always have...
Delta function.
Now, there is no delta function as... There is no... Well, the point charges do not exist, as we know. But it's only approximation. Like, for example, Earth is point-like when you describe its motion around the sun. But in reality, Earth is not point-like. So the same with point-like charge. It's only approximation in which you... So here, general relativity in the very vicinity of this guy is not applicable. How do I understand that? I know that general relativity is following from this action. Following from this action. But that action essentially is part of expansion in terms of powers of curvature. And so general relativity loses its applicability when invariants like this are blowing up. So when this guy becomes huge, you cannot use already this action. You should take into account other things. So in the very vicinity of the singularity, you have to take into account some other theory which includes general relativity as its own part. But we don't know which theory, and actually we don't yet know at which vicinity of the singularity we should use it. But we know that there should be something else. Okay. And
In general, people write 5 tons apart.
yeah. Well, yeah, people...
And maybe I can ask you the real question from the about the previous. You previously said that gravitational field does not carry the energy. You mean the stationary gravitational field, or?
No, I didn't say that.
But what about gravitational waves?
No. I didn't say that gravitation. I cannot define the energy. I cannot define energy when I have a generic curved background. General curved background. If I have a background which is not asymptotically flat, there is no time translation invariant. Energy is something which is conserved as a consequence of time translation invariance. If I don't have time translation invariance, I cannot define energy.
Even for the stationary field?
For the stationary field, I can define because there is time translation invariance. But that's very specific field. Generic gravitational fields are not time dependent.
Yeah, I have a question, maybe related somehow to the earlier discussion. So the entropy of the black hole, according to the Wittgenstein
yeah, we didn't get to that.
theory, is proportional to the area of the black hole.
Okay.
So while naively one would expect, as for other matter, just to be proportional to the volume, can you give a simple
Explanation.
qualitative explanation of that?
Why it is proportional to the...
To the area.
Well, people now believe that entropy of the black hole, actually it's also, you can introduce temperature and entropy of the black hole when it is big enough. When it is very small, probably Hawking radiation is so rapid that you cannot even, Hawking derived his effect in some approximation. It loses its approximation of the black hole small. But in any case, nowadays people believe is that Bekenstein-Hawking entropy is the result of entanglement between quantum fields here and here. For local quantum fields, entanglement happened in the vicinity of the horizon. So that's the reason it's proportional to the area of the horizon. For local fields, entanglement is gained at the horizon. So that's the reason entropy is proportional to the area.
So nothing happens inside the cigar.
No, no. Well, what do you mean nothing happens? There is a lot of things happening. We don't. What do you mean nothing happens?
The holographic principle is that some of the
Explaining these things through the holographic principle is the same as explaining to me puzzle through the mystery. I mean, I don't know the limits of applicability of the holographic principle. The only place where it works perfectly is n equals 4 supersymmetric quantum field theory related to IDS5 times S5 supergravity.
Well, I have to interfere because we have a type of important thing, lunch.
Yeah.
Thank you for the lecture.